Hello, and thank you for watching this screencast. This is for our honors calculus class discussing using the first and second derivative tests to sort of explore the graph of a given function. The assignment that you guys are going to be working on in class while I'm out at retreat is on Delta Math, one of questions from that assignment rather is on your screen here. So I just want to walk you through it and to show you exactly what to do. Your first couple of steps are going to be just find the first derivative, which we'll do here in blue. 3x squared minus 48x minus 51. Again, just simply using power rule there since it's a polynomial function. And then here in red, we'll find the second derivative. Now, if you're a little rusty on that, all you can do for the second derivative is just find the derivative of the derivative. Okay, so in this case, that'll be 6x minus 48, pretty straightforward. And you'll notice that with these polynomials, the original function being cubic, then the first derivative is quadratic and the second derivative is linear. Okay, and just like we did in class, going back to probably Monday's class of this week for you guys, we're just going to set the first derivative equal to 0 to find those critical points. Okay, so if we've got 3x squared minus 48x minus 51 equals 0, I noticed that all three of those are divisible by 3, which probably means this is very factorable. I won't have to end up using the quadratic formula. And let's see, I want to say 16x, and there's 17. So we'll have x minus 17 and x plus 1, which means that my two critical points here are going to be x equals 17, negative 1. And then as we talked about in class, I want to split up, partition the domain of this function, which the domain of a cubic function at this point you guys should know is all real numbers. I'm going to partition it up into three segments here, and then find the signage of the derivative in each of those places. So like, for example, we've talked before about how you could plug in easy enough numbers. You could plug in, for example, negative 2 would be over in this region to the left. So if we found f prime of negative 2, then we'll end up with a negative number, we'll end up with, let me do the arithmetic real quick. Negative 2 squared is 4 times 3 is 12, and negative 2 times negative 48 is going to be positive 96. And so that certainly is going to be positive. Okay, good. So greater than 0. What that means then is that the function itself is increasing. Okay, it is increasing up till negative 1. And if we plug in 0, like if I said, hey, what's f prime of 0? That's going to be negative because, again, we do the arithmetic. We get 0 minus 5. That's a negative number. So in that case, the function is decreasing. And then just similarly, I won't take the time to plug in a large number right here, but similarly, f prime on the far right-hand region, like if I plugged in x equals 18 or 20 or something like that, f prime of one of those numbers is going to be back to being positive, and therefore the function itself, x, is going to be increasing. So we've got the intervals over which this function is increasing. Now let's jump in and do the same thing for the second derivative, and that'll tell us the intervals over which this function is concave up or concave down. So the second derivative, 6x minus 48, if we set it equal to 0, okay, again, this was divisible by 6, so that makes it kind of nice, x minus 8, so it should be obvious that x equals 8. And then on a number line again, right here, here's my number 8. And then to the left, I'm going to pick a value, plug it in. So 0 is easy enough over here. So the second derivative of evaluated at x equals 0 is going to be, that would be plugging in 0 right there. So it's going to be negative less than 0. So what that means is that our function f is concave down on that region. Okay? And then if we picked a positive, or rather picked a number greater than 8, so like f double prime of 9, let's just say. Okay, so 9 times 6 is 54. 54 minus 48 is positive. So with that being positive, what we know then about the function is that it is concave up. Okay, and so now using these two number lines as sort of a guide for partitioning off the domain of this function, we could now answer the question, okay, where is this function increasing and concave up? Okay, so if I were to superimpose the red line and the blue line over here in my black box, if I were to superimpose one on the other, okay, I would have -1, 8, 17, okay, and I would have increasing, decreasing, increasing, concave down, concave up. Just arrow, I guess. And then increasing, decreasing, increasing, to kind of look at it that way. What do we want? We want the area of my number line where it's both increasing and concave up. So that would be from here over. You can see that both of those are happening. So in other words, what we're looking for is where is the first derivative positive and the second derivative positive. That's what we were really looking for. And there's no other place where that occurs, because the only other region of my domain here where it's concave up at that same point between 8 and 17, the first derivative is negative, so the function's decreasing from there. Now, the way that you're going to enter these in, so I would say from this point forward, 17 to positive infinity, the way that you guys are going to enter this in is you're going to use that sort of set notation, right? So in this case, what I want is from 17 to infinity. And the only other question I'll have, and I'm going to actually I'll be the guinea pig for you guys, is if we want a hard, a closed, sort of inclusive left side there to our set. I've got a feeling that it might want that. Parentheses as opposed to that bracket. And then, of course, they're going to walk you through everything that we just talked about. And there's our final answer. And my last comment would be just looking at the graph. Okay, looking at the graph of this function, this cubic function's curve, we can very easily tell where it's going up from left to right and where it's concave up. In the middle right here is what's called an inflection point. That's where the function changed in its concavity. Down here is where, down here is where we have the critical point, okay? And so we can tell that it's concave up and increasing only over here from 17 to the right. So anyway, I hope this makes sense to you guys. Y'all will have some work to be doing on this here in your classwork since I'm out on retreat today. And if you have any questions, you can bring those to me tomorrow in class to end our week. Thanks again for watching and have a great day.